This video is on exercise 9A challenge question of A-level Maths Pure 2 textbook. This question is about showing from first principles that the derivative of sine kx is k cos kx. And we know from Pure 1 that if we want to prove something by first principles, this is the way we do this. So we know that the derivative of a function is equal to the limit of f of x plus h minus f of x over h as h tends to 0. So this is the way that we should show the derivative of a function by first principles is what. And now in this case we should be careful because our function is sine, and here we have kx, so this is not sine x, this is sine kx, so this is going to be important. Now we can start by writing down f dash x is equal to the limit of, now here is the important bit. So since our function is sine, we write sine, then sine kx plus kh minus sine kx over h as h tends to 0. Yeah, in this question, this bit is quite important to note that here should be kx, kh, and here is also kx. As a result of that, because our original function is kx, so that's why here we substitute kx. Now for the next step, we should use the addition formula of sine a plus b. F dash x is equal to the limit of, now here so we know that sine of a plus b is equal to sine a, so let's just write that down here, it's fine. From Pure 2 we know that sine a plus b is equal to sine a times cos b plus sine b times cos a. And now here is exactly what we are going to use. So sine kx times cos kh plus sine kh times cos kx minus sine x, this term, minus sine kx, which is this term. And yeah, also we have h in the denominator as h tends to 0. Right, now here we can factorize. Hopefully you can notice that we have here sine kx term and also here sine kx term, so we can take a factor of sine kx out and see what happens. So f dash x is equal to the limit of sine kx, so here we will have cos kh minus 1 and plus this term because we haven't factorized that, plus sine kh times cos kx over h as h tends to 0. Right, now here is the important bit, and we have now got to the point that we can use these two facts, because the question has given us that cos kh minus 1 over h tends to 0 as h tends to 0, and same thing with this, so sine kh over h tends to k as h tends to 0. And here hopefully you can see that this is exactly the same thing. So here we have cos kh minus 1 over h, and here we also have this term, but if we split this fraction into two fractions, then that's going to make more sense. So I'm going to do that in a second just to clarify what I'm saying. So limit of, now we can split this fraction into two fractions, so sine and let's put the whole thing inside the bracket, so sine kx times cos kh minus 1 over h plus sine kh times cos kx over h, because we are completely allowed to do this. Now hopefully you can see that this is the term I was talking about. So here was cos, and yeah, I wanted to highlight this. So this bit is the term, and since this is multiplication here, so we are allowed to treat this as a separate term. I mean, when we want to do operations. And the other one was sine kh over h. Yeah. And now you might be asking that why, as h tends to 0, this tends to 0, and this term tends to k. Now I can show you that, even though you don't need to show that in your proof, because they've already given you this, and you can simply now use this as a fact. But now I'm just going to show you for just for your understanding. But again, you don't need to include this bit in your proof. So because there's one extra step that they don't want you to do at this question. So yeah, f dash x is equal to the limit of. So now we need to remember something, and that's called actually we need to remember the small angular approximation. So that's the thing we need to remember, because by the question we know that h tends to 0, which means h is very small, so that we are allowed to use the small angular approximation. And also on the other hand, here you can see that we have sine kh. So by a small angular approximation, let's just write that here, we know that sine theta is approximately equal to theta, given that theta is a small, and cos theta is equal to 1 minus theta squared over 2, given that theta is a small. Now we can use these two approximations in order to continue the question. So limit of sine kx times, now let's use the apply the small angular approximation for this highlighted bit. So cos kh, if we use that, because kh is the thing that is going to be affected by the formula, so according to the small angular approximation here, we are going to have k1 minus kh squared over 2 minus 1. This minus 1 is just from this term, over h. And the next bit, so let's use the small angular approximation for this highlighted bit. So sine kh, according to the small angular approximation, sine theta is approximately equal to theta. So kh is equal to sine kx is equal to kh times cos kx, which is just this term, over h. Now we can simplify some of these. So f dash x is equal to, as h tends to 0, so it's very important. Yeah, you can obviously write this first so that you won't forget that. Now sine kx times 1 minus k squared h squared over 4 minus 1 divided by h plus, now here we can simplify this straight away because this is multiplication, so this h cancels out with this h in the denominator, so that we have k cos kx, and we need to now simplify this bit. So we have 1 and minus 1, so they cancel out here, and also this h cancels out with this power of h, which is in the numerator, and now we will only be left with k squared h over 4. So now hopefully you can realize that h is very small. H approaches 0, which means when h is approaching 0, then 0 times k squared over 4 is just 0. And 0 times this term sine kx is also 0. So that's why this term on the left hand side, the whole thing tends to 0 as h tends to 0, because h is very small. So yeah, this is just a limiting behavior, and you haven't learned about this in a formal way and proper way. And yeah, so that's why this just the left hand side tends to 0, because this bit tends to 0, and 0 times this is also 0. So that's why just the left hand side is going to be 0. And now we will only be left with k cos kx, and that's exactly what we want. So f dash x is equal to the limit of since now we have applied the limit, now we don't need to write down the limit again, because now we've already applied that. We've already considered what happens to the whole thing as h tends to 0. Now we just need to write down f dash x is equal to k cos kx, because just this whole thing that I'm now highlighting, this is just 0. So here is 0, and then this bit is what we want. And that's it for this question. So thanks for watching, and please consider subscribing for more videos. Good luck.